Patrick Gérard, who needs no introduction in this crowd of certified PDE analysts, CPAs. So, Patrick, the floor is yours. And one more thing, since I've heard a part of this talk, I can tell you that you are up to a real treat.
Thank you very much, Eitan, for this kind words. I'm very pleased and honored to be here. Thank you very much for all of you who organized this beautiful meeting. Today I'm going to talk about integrable PDEs. So essentially it's a very interesting topic, except that nobody knows exactly what it is. But if you ask Percy Dave about this, it will tell you an integrable PDE is a PDE that you can integrate, which means that you can solve, which means that you can find an explicit formula, and that will be, in fact, one of the topics of my talk today. I've been working on integrable PDEs for quite a while, for 15 years. And I switched to them because I realized that with these additional structures provided by Lax pairs, you can usually access to information which is not possible to describe in the classical cases. So these special PDEs and these special structures give us answers typically to problems of growth of Sobolev norms, as we saw with the talk of Enno Lenzmann yesterday with the Calogero-Moser DNFs. So today I'm going to talk about a rather classical integrable PDE, which is the Benjamin-Ono equation. And to illustrate this principle that I try to describe, I'm going to discuss a notoriously difficult problem, which is a problem of small dispersion limit, or zero dispersion limit. In dispersive equations. And for this, I will need an explicit formula and to give a somewhat general answer for this problem of zero dispersion limit, I first, of course, need to introduce the equation. So the equation is the Benjamin-Ono equation, introduced by Brooke Benjamin in 1767, so at a time when several of you were not born, probably. And so, and then there were different people who worked, in particular Ono from Japan, studied a lot the question of traveling waves. And I wrote this equation under the Hamiltonian form. Here, this dx is the j of the Hamiltonian structure. This is the gradient of the energy. U is a real valued function. X is a real variable function. And U is supposed to be 0 at infinity, so it will be in Sobolev spaces. And mod dx, as usual, is a multiplier by absolute value of xi. So this dx, mod dx, is really your favorite dx square, except that we are working with real variable functions, and to have something which is anti-self-adjoint, we have to deal with this dx and this mod d. Okay. Usually you see this rather than dx square times the Hilbert transform, but since they are very different notation, and for the Hilbert transform, I prefer this notation. So I will not discuss the rigorous derivation of this from the water wave system by long wave approximation, etc. Infinite depth. This was done in quite a general context by Jerry Bonnard, David Ladd, and Jean-Claude So 15 years ago. But I will just review for you it's not so important, but okay, it's the opportunity to tell you that this equation has really what was the center of many different problems with many different people in analysis. So probably the first result on well-posedness was by Jean-Claude So for well-posedness, global well-posedness in H2 of R. Then tau broke some wall in 2004 by introducing some nice normal form for solving this equation in H1. Then Ionescu Koenig went further. In L2, there is also a nice proof by Mihaela Freeman, Daniel Tataru. And recently, Monica Vision, Rowan Killick, and Thierry Lawrence, he is from Belgium, they went up to the scaling threshold, which is h minus a half using the Lax pair, which means, of course, this equation doesn't have a meaning for functions which are hs for s negative, but the meaning is given by the continuous extension of the flow map. So you have a nice flow map defined by so on H2 on smooth and decaying data, and it can be uniquely continuously extended to HS for every s bigger than minus a half. This is the content of Killick-Lawrence Vision theorem. And they use, of course, this Lax pair structure, which will be in the center of my talk and which was discovered by different people. For periodic boundary conditions, I will not talk about periodic boundary conditions here. The nice result by Luc Moliner was about well-posedness in L2, and then you have the optimal result by Thomas Kappeler, Peter Topalov, and myself in 2020, for proving there is no well-posedness in H minus a half, but well-posedness in HS for every s bigger than minus. Okay, so this is the general landscape of well-posedness. I'm not going to talk about it. I'm going to talk about another problem, which is the problem of small dispersion limit. So I just take the same equation. I put this dxu square in the left-hand side. So this looks like the beginning of the Burgers-Hopf equation. And I put an epsilon in front of the dispersive operator. So if you remember the talk by Jalal yesterday morning, this is a little bit different, you know. I put nothing in front of the nonlinearity, but I put epsilon in front of the dispersive operator. Jalal did exactly the other way thing. But of course, I will be interested in finite time, not big time. Okay? But still, this is well known to generate strange things. Why? Well, even if you don't know much in hyperbolic problems, you probably already encountered this equation dtu plus dxu squared equals 0. This is the implicit of Burgers equation. And you know that even if you start from very smooth and very nice data, it will develop singularities, which are shocks. And this you can see by studying the method of characteristics for this equation. So what happens when epsilon goes to 0? How this u epsilon come close to the solution of the solution of the Burgers-Hopf equation? And is it really, the limit, if it exists, a solution of the Burgers-Hopf equation? The answer is, in general, no, it's not a solution of the Burgers-Hopf equation, because u epsilon will develop oscillations, very strong oscillations, so that even if you have an L2 bound on u epsilon for all time, which is given by the conservation law, the convergence in L2 cannot be strong. Okay, so this is what I said. Okay, if tau is t is small enough and u0 is smooth enough, of course there exists a smooth solution to the Burgers-Hopf equation, and it's easy to see that the convergence in that case will be perfectly nice. But what I'm really interested in, the limit of u epsilon of t, if it exists, after the time of shock formation. Okay. So this is a very simple problem to state. All right, so I'm going to answer this question today. Of course, I'm not the first one who studied that kind of problem, particularly there is a long-standing problem connected to the court-effective Breeze equations, and this started with a famous series of papers by Peter Lax and David Livermore. And then Venakines, Dekt, Zhao, Venakines, Zhao, Claes, this is, sorry, E is before Y, Claes and Gravard. They studied this by inverse scattering theory. Why? Because you certainly know that court-effective Breeze equation is one of the most famous integrable PDEs, in the sense that it has a Lax pair, because Lax founded this in 1968 in his seminal paper in CPM. And when Peter Lax had a nice PhD student, David Livermore, he asked him to look at this problem using the inverse scattering transform for finding the limit, the zero dispersion limit of KD. And this was, in fact, the beginning of a series of very interesting papers, but very difficult to read, if I may, because you need to be introduced to inverse scattering theory. And this is some kind of yoga, which is so, okay. And moreover, the results necessitates quite stringent assumption on the datum. Because before doing inverse scattering, you have to do direct scattering. And direct scattering for an operator like a Schrödinger operator on the line demands some decay on the potential, just to construct what are called Yost functions. Yost functions are very important generalized eigenfunctions, but you need some decay, typically L1 decay, for your potential. If it's not, well, you have to work much more. And these people did not want to, because it's already very complicated. There were numerical approaches, particularly by Tamara Grava and Christian Klein. There are much others. And in fact, preparing this talk, I found that there is a master thesis which was done in NTNU, in 2013, under the supervision of Edgar Howden. And he told me, he confirmed, this guy, Fixdal, wrote a master thesis on a numerical approach of the small dispersion limit for Benjamin-Ono equation. He found a lot of oscillations. And he said, okay, the weak solution, if you start from the characteristic function of an interval, the weak solution does not look like the entropy solution, the Lax or Leinik entropy solution. It looks like something more continuous. It seems that there are no shocks anymore. We'll see. So there are some results by Peter Miller, who used to be a PhD student of Livermore, and who is now a professor in Michigan, and his collaborators, Shu and Welzer, and more recently by my former student Louis Gassot in the periodic case. Using the inverse spectral theory or inverse scattering, it's still possible, but again, with very, very specific data, typically 1/1 plus x squared on the line, bell-shaped data. Okay, so I'm going to revisit this problem today for you. And I'm going to bypass completely inverse spectral theory, which may be a bad news for some, but I think good news for me. All right? So that's what I'm going to do. So before this, I'm going to talk about the method of characteristics. Now we come to the slide which required maybe more time to me. So this is the method of characteristics. So this is if you start from an initial datum U0. So if you solve the smooth part of the Hopf-Rögers equation, and so you look at the characteristics, x dot equals u of t x of t, then you get that this guy is a constant along the characteristic, and as a consequence, the characteristics looks like this, okay? So now if you are given a function, a point t and a point x, a time t and a point x on the line, you may want to find all the characteristics which are lines, y plus 2t u0 of y, so y is the starting point of the characteristic at t equals 0, such that at time t, the characteristic is x. So this means that these are three different graphs of this function y gives y plus 2t u0 of y, which is again the characteristic starting at time at time 0 from y, and the characteristic at time t. And you ask whether this x can be y plus 2t u0 of y. So for instance, for the blue line, which corresponds to a small time, there is always exactly one characteristic corresponding to x. For the green line, it depends, okay? And there might be several, but here there is just one. And for green line, which corresponds to big time, then for my x, there will be three different characteristics which will cross at time x, okay? And this implies oscillations. So this is exactly the zone where you have several characteristics crossing. Outside of this zone, there is just one characteristic. Okay? And what I'm interested in is what's going on here.
So this is for the bell shape.
This one is a bell shape, but in fact you will see that it's in fact much more general than this, with of course different zones. But this is typically for the bell shape, yes, I agree. So this is the main result. So I take any function u0 in L2 and in infinity. So this is my initial data. I take that for every time t, the solution u epsilon, which depends on t, of this equation with this initial data and this epsilon dx here, is weakly convergent in L2, which is already something. You prove that you have weak convergence. You don't have to extract a subsequence. Of course, it's bounded in L2, so there is a subsequence such that. But in fact, any weak limits is the same. There is just one weak limit, and we are going to compute it. So I'm going to compute it in the special case of a rational function, but in a rational function of any degree. u0 is just p of y divided by q of y, a real rational function with no pole on the real one, the real line, of course. And I exactly do this thing. I pick a t and x, and I look at the equation y plus 2t u0 of y equals x. Sorry. So remember, this u0 is a rational function, which means that it's the quotient of a polynomial of degree at most 2n minus 1, and a polynomial q of degree 2n, because it cannot have a 0 on the real line. And so if you want to solve this equation has a degree 2n plus 1. Okay, so of course it has solutions by a well-known theorem. But some solutions are real, others are complex. And the real solutions are, of course, an odd number, because the complex ones come with their conjugate. Okay? So let me call this solution the real, and let me assume they are simple. This is generic, of course. Let me call them y0, etc., y2l. And then I claim that the weak limit is given by this formula. U of tx is the alternate sum of the values of u0. What is uk? I'm sorry, uk of tx here is u0. I should have written it, sorry. uk of tx is nothing but u0 at yk of tx. So this is really the value of u0 at the point of the characteristic at t equals 0, which is propagated along the characteristic. So we have two two L plus 1 characteristics arriving at the same point Tx. Sorry, don't see it. So you have Tx here, and you have 2L plus 1. Here it's 3, y0, y1, y2. And you have this u of Tx, which is just the sum from k equals 0 to 2 of minus 1 to the k, u0 of yk. Just this. This is the formula. I wrote this formula for a rational function because I'm going to compute it and using the rational part of u0, but in fact, then it can be generalized to much more general, just by approximation. So this formula was in fact already found in the very special case of the bell-shaped profile by Miller and Wetzel. But what I want to tell you here is that it's possible to generalize it to essentially any kind of data. And by a very different method. So, my talk will be in 3 parts. The first part will be to prove a completely explicit formula for the solution of the Benjamin-Ono for a given epsilon, if you prefer. An arbitrary datum in L2 intersection L infinity. And this will, as I already announced, bypass completely the inverse spectral theory, but it will not bypass the Lax pair structure. I will use very strongly the Lax pair structure in a different way. Second, I'll pass to the zero dispersion limit in this formula, and it turns out it's easy. So I will get a formula, still a little bit complicated, for any data in L2 intersection L infinity. And finally, I'm going to make the link of this formula with the multi-valued solution of the Burgers-Hop equation, which means this alternate sum of values, different values of the Burgers-Hop equation from the method of characteristics. Okay? So let's go. Let's talk about the Lax pair. So for studying the Lax pair, it's extremely useful to introduce the auxiliary Hilbert space for the RD space, which here is denoted by L2 plus of R. Some other people will like to call it H2 of C plus, but H2 is already taken. All right, so this will be L2 plus. So these are functions in L2 such that the Fourier transform is 0 for C negative. And by the Palais-Wiener theorem, it tells you that these are also this holomorphic function in the upper half plane. C plus is just the upper half plane, imaginary of Z positive, such that the supremum of the L2 norm on the horizontal line in the upper half plane is finite. It's Palais-Wiener. Now I have this Ries-Zegel, maybe also Cauchy. Oh, okay, I forgot it. Sorry. The associated Cauchy-Ries-Zegel projector is this guy, just corresponding to multiplication by the characteristic function of the half line in the Fourier transform. And then I'm going to introduce exotic operators. So this one was introduced by Otto Toeplitz before World War I. Toeplitz operator of symbol B, so take any L infinity function in the line, and you define TB, which is the following bounded operator on L2 plus, well defined by, well, just take the product of B and F, and since BF is not in L2 plus, you just project it in L2 plus. In the Fourier transform representation, this is just a convolution with B hat, knowing that the Fourier transform of F is supported on the half-line. And of course, it's easy to see that the adjoint of this bounded operator is just the Toeplitz operator associated to the conjugate. Okay? So this is my basic toolbox, TB. Okay? So now I'm going to introduce the Lax pair. So given a function, let me assume that it's L infinity for the moment. It will be maybe a little less, but let's say it's L infinity. I define the Lax operator L associated to U, which acts on the Sobolev space H1 plus, which is H1 intersection L2 plus into L2 plus, just by this. It's a differential operator of degree 1. 1 over I ddx. Of course, very nice, very self-adjoint, very anything. Not bounded, but still. And bounded from H1 to L2, of course. And minus TUF. So this is, of course, an operator of order 0. It's in some sense perturbation of this nice operator. The very important observation about this operator is that the main part, which is here 1 over I ddx, is a positive operator because we are working on the RD space. So the xi variable, which is 1 over I ddx by Fourier transform, is non-negative. So if you apply the Blanchet formula to compute the inner product of this guy with f, you will get integral of xi, f hat of xi squared, which is positive because xi is positive on the support of f hat, right? So it's easy to see that this is an unbounded self-adjoint operator. Its domain is precisely H1 plus. And you can define for a U which is a little more regular, H2, so again, Sobolev space H2, real than U. You can define this guy, BU, which is a bounded operator and anti-self-adjoint, which is I T mod du minus tu squared. Don't pay attention too much to the formula. They just exist. Just remember they exist. And what is really important for me is this, which is a theorem which was proved by different people in different formulations. That's why there are so many people. So the formulation I use here is the one I wrote with my friend Thomas Kapler. It tells you that if U is a smooth enough solution of Benjamin-Ono equation, then I have this Lax identity, ddt of Lu equals commutator Bu Lu. What is really important is the corollary. The corollary tells you that there exists a family of unitary operator on my auxiliary Hilbert space, L2 plus, such that Lu at time t is conjugated by Lu at time 0 by this family of unitary operator, capital U of t. This is the formula you can find in Lax's original paper in this context, okay? And you just have to solve this ordinary differential equation, linear ordinary differential equation. Remember, Bu was bounded. So Bu of t is continuous in time, valued in bounded operator on my Hilbert space, and this is just a theorem by Cauchy, essentially, which tells you that this linear differential equation is well posed. And since U of 0 is identity, and since Bu at time t is anti-self-adjoint, it's easy to see that U of t is unitary. Okay? So this, what I really require you to have in mind, maybe I'm going to write it down here, is this nice formula. Okay. Now the explicit formula. So I'm going to quote Lax for the third time about the Lax-Berling semigroup on L2 plus. The semigroup of Lax-Berling is something very simple that people from dispersive equation know rather than Galilean transformations. So multiplication by e to the I eta x, except that we are on the Hardy space. So e to the I eta x shifts the support of the Fourier transform, well, by eta, which means that in order to stay in the half line C non-negative, eta has to be non-negative. Otherwise, you go out, you go on the other side, okay? So this is why it's not a group, but a semigroup. Now, its infinitesimal generator is just the multiplication by x, okay? Or ix if you want, okay? And of course, I'm going to look at, well, of course, maybe not, but I'm going to look at the adjoint of it. And the adjoint of the infinitesimal generator is an operator which I call G, like generator, which is x star. And so that the adjoint S of eta is just e to the minus I eta G for eta non-negative. And just to have an idea of what is G, you can use the Fourier representation. G f hat is just I d xc of f hat for xi positive. And the domain of G is bigger than the domain of X, because it's just the domain of function f in L2 plus, such that the restriction of the Fourier transform to the half line is in the Sobolev space, so that this is, of course, in L2. So this means this allows you to have jumps of a Fourier transform through zero. Remember that the Fourier transform is zero for xi negative. If you were in the domain of X, well, you would be in L1, so the Fourier transform would be continuous. So it would be 0 at xi equals 0, since it's 0 for xi negative. But for my guys in this domain, the Fourier transform can be 0 on the one line, half line, and something else on the other line. And G is just the derivative of that part on the other. Okay. And now I'm going to define I plus. I plus means some integral, but from the plus part. So if you have n1 function, f hat of 0 is the integral of f. Here I look at f hat of 0 plus, assuming that, again, I'm in such a situation that f hat, say, on the 0, 1 is in h1. Because in that case, of course, there is a limit as t tends to 0 plus. And now the theorem is as follows. I pick any u0 in h2, say, function of the Benjamin datum, and I look at the solution of the Benjamin-Ono equation. u0 is real valued, so u will be real valued. So I can always write u as twice the real part of its projection. That's easy. Now the problem is to characterize the projection. And now I'm very happy, because the projection is in the Hardy space. So I can characterize it by computing in the upper half plane, for x in the upper half plane. It's a holomorphic function in the upper half plane. And for such a value of x, what do? I take pi u0, which is a projection of my initial datum, and I apply the resolvent of this nice operator. Remember the talk by Eno yesterday? There was some matrix here which were called M0, and you had this 2t sum L. And then you invert this minus x. That's exactly what happens here. Essentially, the role of the matrix M0 is played by my operator G. And then you can prove, just by standard semigroup theory and perturbation, and this is why I really need u0 to be an infinity. Here it's even better. You have to prove that this guy has this property, that the Fourier transform of this guy, this image by the resolvent is in H1, and then you take its I plus and 1 over 2 I pi I plus. Okay, maybe let me write it down just for a while. The solution of my Benjamin-Ono equation. So I take pi u0 and I apply to it the resolvent of this operator, G minus 2t lu0, and then I take 1 over 2 I pi of I plus of this. And this is pi u of tx. This resolvent is well defined because the imaginary of x is strictly positive. Of course, we are interested in what's going on for x real, but if you know a holomorphic function in the upper half plane, you know its trace on the real line. And that's the trick. Okay, now, how to prove this? Well, I'm going to be, yes, a little sketchy. But I would really like to show you some very elementary thing which is how to write the inverse Fourier formula in the Hardy space. So I take a function f in the Hardy space here, and I introduce some cutoff function which is an approximation of 1 as epsilon goes to 0, and which is also in the Hardy space because the pole is minus I over epsilon. It's in the lower plane, so it's a perfectly holomorphic function for a given epsilon positive in the Hardy space. And now I write some, I think, well-known formula, but for x in the upper half plane. So this is the inverse Fourier transform in the Palais-Wiener context. So this is a perfectly well convergent, absolutely convergent integral because the imaginary of x is positive and xi is positive. And then I replace f hat of xi by its value, which is a limit in L2 by the Blancherel theorem. Remember that Blancherel, prove this theorem just by saying that I have a limit in L2 of L dot something, the Fourier transform of f times something, which is, so that this is for a given epsilon is in L1. And then I recognize that this is an inner product, the inner product of f with what? With S of xi, the Lax-Berling operator acting on key epsilon. Again, S of xi is just e to the ix xi. And then I put this S of xi on the other side, S of xi star. I interchange the inner product on x and the integral in xi. I put it inside. I replace S of xi star by definition by e to the minus I xi g. And then I compute the integral in xi. I get this. And this is in fact the inverse Fourier formula. F of x equals 1 over 2 I pi I plus g minus x minus 1 f. Which means that the formula I wrote on the whiteboard is correct if t equals 0. Okay? Because I say pu0 of x equals pu0 of x. Well, that's true. Now what is really interesting is to deform this formula with the time. And I have an object, a secret weapon, to deform such thing with the time. And my weapon is ut, u of t, the guy unitary which conjugate LU at time t to LU at time 0. So since this formula is finally nothing else but an inner product, I'm going to apply the unitary operator u of t star to both sides of this inner product. If I do this, I will see u of t star acting to key epsilon, u of t star acting on f, which will here pi of t. And I will see u of t star g u of t. And the miracle is that I can compute all these guys explicitly in terms of u0. And this is the miracle of the Lax pair. So let me show you one typical calculation. I'm going to compute u of t star g of u of t. Well, this is since u of t satisfies this differential equation, this is just u of t star, commutator gb of t, u of t. But now you observe a very important commutator identity. The commutator of g with the second member of the Lax pair, du, equals minus 2, the first member, lu, plus I lu squared g. And moreover, of course, you know that LU of t, this is what I wrote on the pad, the iPad, ut of star, L of t, u of t equals L of 0. You get, if you replace GBU by that, applying this, you get and you can integrate this differential equation and you get this. So it only depends on t and u0, my initial datum. Then you plug that kind of formula in the previous formula here. You can do also the computation of u of t star, pu of t, etc., etc., and you get finally this formula here, which is this one. So it's not a big deal once you have understood the real importance of the Lax pair members. Okay. Now the zero dispersion limit is the same, except that you have to make a small rescaling to get the same Benjamin-Ono equation with epsilon in front of the dispersive part. So remember, my equation was this. So this is my equation. So you can easily find that u epsilon at tx is just 1 over epsilon v of epsilon t and x, where v is the solution of Benjamin-Ono with data 1 over epsilon tx is 1 over epsilon this. Oh, sorry, this. With v of 0 and x equals u0. Okay? So no, sorry, it's this. Yes. And this. This is a scaling. In other words, this is a scaling change, t change epsilon t, and u change u over epsilon. If you do that in the classical Benjamin-Ono, you get the Benjamin-Ono equation with an epsilon. But now you can apply the formula we found to this situation, and you get a formula for pu epsilon. You just replace u0 by u0 over epsilon and t by epsilon t. But remember, Lu is 1 over I ddx minus Tu. So if you put epsilon t Lu0 over epsilon, there will be two terms. This term, epsilon td, and this term where there is a cancellation, epsilon 1 over epsilon, which gives you Tu0. Aha! But now, when epsilon goes to 0, it's not a big deal to prove that this resolvent converges strongly to the resolvent with epsilon equals 0. And in fact, it's possible to pass to the limit inside the I plus formula, and this gives you the limit for pu of tx. So this precisely means that you know that there is an L2 conservation law. So you know that there is a bound in L2. So you know that there are weak limits in L2. And what I tell you is that all the weak limits have a pi which is given by this formula. So this means that there is just one weak limit. It's in L2, of course. Moreover, its L2 norm is not bigger than the L2 norm of U0. It's not so trivial to prove, but we know it. And now we have to compute this. And this is what I'm going to do in the last 5 minutes. So since only last 5 minutes, I'm going to do it with a very simple rational function, ay plus b divided by 1 plus y squared. In that case, essentially, and so pu0 is just a constant divided by 1 plus I. pu0 is just, you just decompose this rational function in elementary parts, okay? So now I come back to my method of characteristics here, and I see that essentially this equation, which is a cubic equation, has either one real solution or three real solutions. In the first case, this real solution called U0, Y0, and the other are complex and they are conjugated. Let's say that the second one has imaginary part positive. And in the second case, they are all real. Now imagine, this is for x real. Imagine that I switch a little bit x in the upper half plane with a small imaginary part. How do these solutions behave? Well, this is the implicit function theorem. I know that. Plus the Cauchy-Riemann equation. I know that the derivative of the imaginary part of an holomorphic function with respect to the imaginary part of the variable equals the derivative of the real part of the holomorphic function with respect to the real part of the variable. This is Cauchy-Riemann. So it tells you that if x is slightly shifted in the upper half plane with imaginary fx strictly is positive but small, the imaginary part of y0 will be positive, the imaginary part of y1 will be negative, and the imaginary part of y2 is positive. Why? Because you have this picture, okay? Up, y0, y1, y2. So the derivative here is positive, here is negative, here is positive. So this is precisely the sign which will give you how it goes, the imaginary part is goes, by the implicit function theorem in Cauchy. So the zeros in the upper half plane are y0 and y2 of this function, which is a fundamental characteristic equation. Now, the miracle comes. I'm going to solve this equation here. I mean, not exactly this one, but the one with TU0, remember? The formula for my PU is this one. So I have to inverse G plus 2t TU0 minus x acting to pi u0, which is a rational function. And I claim that the whole guy here is a rational function. This is a miracle. It's always the case. And so I can compute this rational function because I know how rational function acts on rational function by way of Toeplitz operators. That's essentially a product plus some remainder term which will correct the bad pole y equals I. And in the same way, the action of G is just, well, that's just the derivative of a function which has a jump, which is 0 for xi negative and something for xi positive. So by Schwarz's formula from distribution theory, it is exactly the derivative for xi positive plus the jump times delta 0. Since this is in the xi variable, if you take the inverse Fourier transform, you will get just a constant. This constant is precisely 1 over 2 pi plus f. Now you plug everything in the equation, and this is the equation. You get a rational function, and the constants here are unknown, which are fitted so that f is holomorphic in the upper plane, is in the Hardy space. And this just tells you that this right-hand side should cancel here when the left-hand side cancels. This is a 2 by 2 linear system that we can solve. Wow. And when we solve it, we find a very nice formula for lambda, y0 minus y2 minus x minus I divided by 2i. Now what is interesting is really that pi u is 1 over 2i pi I plus, and it turns out that this is exactly minus lambda. So now if you take the real part of this, you get that, blah, blah, blah. And finally, in case 1, you get u of tx equals u0 of y0 of tx, and in the other case, you have the alternative. This simple formula can be carried out for every rational function of degree n. Well, you have to make a few more calculations. You have to use the collaboration of Cauchy and van der Monden in the theory of determinants. And you get a big n by n determinant divided by another big n by n determinant equals something of that kind. It's a little bit miraculous. Okay, just my last slide. What are the perspectives? This formula I wrote for rational data with the alternate sum of branches of solutions of Earth curves. It in fact extends to many more general data, typically H2 functions. It's enough.